We shall now discuss about determinants. But first, we define the permutation of a set S. Let S be a set consisting of the numbers 1, 2, up to n in ascending order. A permutation J1, J2, up to Jn is a rearrangement of the elements of S. The elements could either be some or all elements of S. So we shall denote the permutation by the symbol J1, J2 up to Jn. So example is S consisting of the numbers 1, 2, and 3. We list down all the permutations of S. Since there are 3 elements, we shall denote any of the permutations of S by J sub 1, J sub 2, and J sub 3. The arrangement 1, 2, 3 in itself is a permutation of S. Another permutation is 1, 3, and 2. Another is 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. So all in all, S has 6 distinct permutations. Alright? How about for S equal to 1, 2, 3, and 4? Will you list down all the permutations of S? List down all the permutations of S. Okay. So let us rewrite the elements of S: 1, 2, 3, and 4. So the permutations of S will be denoted by J1, J2, J sub 3, and J sub 4. We can list down all the permutations beginning with number 1. So 1, 2, 3, 4, 1, 2, 4, 3, 1, 3, 2, 4, 1, 3, 4, 2, 1, 4, 2, 3, 1, 4, 3, and 2. Okay? Then, all permutations beginning with the number 2. So 2, 1, 3, 4, 2, 1, 4, 3, 2, 3, 1, 4, 2, 3, 4, and 1, 2, 4, 1, 3, and 2, 4, 3, 1. Next set, permutations beginning with 3. With the number 3. So 3, 1, 2, 4, 3, 1, 4, 2, 3, 2, 1, 4, 3, 2, 4, 1, 3, 4, 1, 2, and 3, 4, 2, 1. Finally, those permutations that begin with the number 4. So J1, J2, J3, and J4. 4, 1, 2, 3. 4, 1, 3, 2. 4, 2, 1, 3. 4, 2, 3, 1. 4, 3, 1, 2. And 4, 3, 2, 1. Okay, so all in all, there are 24 permutations of S equal to 1, the numbers 1, 2, 3, and 4. At this point, let us derive the formula on how to find the number of distinct permutations for n elements. So we will try to answer how many distinct permutations are there in n distinct objects or n distinct numbers. So your S here is from 1, 2, 3, up to n. Okay. So for S equal to 1, 2, 3, 4, there are 24 permutations. No? 24 permutations of S. So there are 4 positions that we need to fill up. No? For the first position, we have the choices 1, 2, 3, and 4. So we have 4 choices for the first position. For the second position, since we have already filled up the first position, there are only 3 choices left for the second position. And filling up the first 2 positions by 2 elements of S, that makes 2 choices. That allows us to have 2 choices for the third position. And since we have already filled up the first 3 positions, there is only 1 choice left for the fourth position. Okay? For the first, there are 4 choices, and for each of these, there will be 3 choices for the second position. And for each of the first 2 positions, there are 2 choices for the third position. And for each of the first, second, and third positions, there is 1 choice for the fourth position. So, in other words, we simply multiply 4, 3, 2, and 1, and that will give us the total number of permutations. So applying this to S equal to 1, 2, 3 up to n, the number of permutations will be equal to n times n minus 1 times n minus 2 times and so on and so forth times 2 times 1, or this is abbreviated by the symbol factorial. So there are n factorial distinct permutations for S1 up to n. Alright? So, if S is from 1, 2, 3, up to 5, then the number of permutations of S will be equal to 5 factorial. And that is equal to 5 times 4 times 3 times 2 times 1. And that is equal to 120 permutations. Okay? Now, to find also the number of permutations, we can use the tree diagram. So let us consider the same set S containing the numbers 1, 2, 3, and 4. So for the first position, we have 4 choices. Alright? And what are these choices? 1, 2, 3, and 4. If the first choice is the number 1, then that leaves us 3 choices for the second position. And what are these numbers? 2, 3, and 4. Okay? So if the first number is 2, the choices you have for the second position will be the numbers 1, 3, and 4. Okay? So you do that for the other 2 branches, 3 and 4. Okay. So going back to the first branch of 1, branching out to 2, 3, and 4. For the next position, this will branch out further into 2. And what are these? The choices here are 3 and 4. Alright? If you have the branch 1 going to 3, there will be 2 choices there, which will be 2 and 4. And we do that for all the rest. Okay? So let us continue with 4. That will branch out to 2 and 3. Okay? So for the main branch 1, you now have how many? 1, 2, 3, 1, 2, 4, 1, 3, 2, 4, 1, 4, 2, 3. Okay? And then finally, for this route, 1, 2, 3, there will be one choice, and that will be the number 4. Okay? For the next one, 1, 2, 4, it will end at 3. Next, 1, 3, 2 will end at 1, 3, 2 will end at 4. And 1, 3, 4 will end up at 2. 1, 4, 2 will terminate at 3, and 1, 4, 3 will terminate at 2. So for this main branch 1, how many do we have? 4, 1, 2, 3, 4, 5, and 6. That is for the main branch 1 alone. There are 6. And we do that for the other 3 branches, 2, 3, 4. So if there are 6 sub-branches for 1, and there are 4 main branches, that will be 4 times 6 equal to 24 permutations. Alright? Next, we define an inversion. When does a permutation have an inversion? A permutation J1, J2 up to Jn is said to have an inversion if a larger number J sub s precedes a smaller number J sub r. Okay? So if in the permutation there is a large number preceding a smaller number, then that will count as one inversion. So let us have an example. I'm trying to preserve the permutations of S, no? Containing the numbers 1, 2, 3, and 4 because we will use that later. So, supposing that S contains the numbers 1, 2, 3, 4, and 5. And you are given the permutation 3, 4, 1, 2, 5. Okay? So S is the set of the numbers 1, 2, 3, 4, 5, and 3, 4, 1, 2, 5 is a permutation of S. Let us count on the number of inversions. Alright, we can start with the number 3. 3 is followed by 4, that is in its natural order, so there is no inversion. 3 precedes the number 1, and 3 is greater than 1. So that is already one inversion. Okay? Now 3 also precedes the number 2. Again, 3 is greater than 2, so that is another one inversion. That is another one inversion. Okay. So for the number 3, there are 2 inversions. Now, as far as the number 3 is concerned, there are 2 inversions, 3, 1 and 3, 2. Okay? So, how about the number 4? So, for 3 alone, there will be 2 inversions. 2 inversions. For the number 4, 4 precedes the number 1, and 4 is greater than 1, so that is one inversion. 4 precedes the number 2, another inversion. 4 precedes 5, that is in the natural order, so there is no inversion. So as far as 4 is concerned, there are 2 inversions. So for 4, there are 2 inversions. How about 1? 1 is the smallest among the digits 1, 2, 3, 4, and 5. So there will be no inversion as far as 1 is concerned. For 2, 2 precedes 5, and 2 is less than 5, so there will be no inversion. 5 itself will have no inversion. So all in all, for the permutation 3, 4, 1, 2, and 5, there are 4 inversions. Right? So will you try counting on the number of inversions for the following permutations? 4, 3, 5, 2, and 1, 5, 4, 1, 2, 3, 2, 4, 3, 5, 1, and 3, 1, 4, 2, and 5. Okay. So for 4, 3, 5, 2, 1, 4 precedes 3, that is 1. 4 and 2, that's another 1. 4 and 1, that will be 3. Okay? So 4, 3, 4, 2, and 4, 1. Next, 3, 2, and 3, 1. So that's another 2. 3, 2, and 3, 1. 5, 2, and 5, 1. That's another 2. 2, 1, that is another 1. So all in all, that will be 7, 5, 7, that will be 8 inversions. Okay? 4, 3, 4, 2, 4, 1, 3, 2, 3, 1, 5, 2, 5, 1, and finally 2, 1. Next, 5, 4, 1, 2, 3. 5, 4, 5, 1, 5, 2, and 5, 3. That will be 4. Again, 5, 4, 5, 1, 5, 2, and 5, 3. Next, 4, 1, 4, 2, and 4, 3. So that will be 3. 1, 2, 3 is already in its natural order, so there will be no inversion there. So 4 and 3, that will be 7. Next, 2, 4, 3, 5, and 1. 2, 4, 3, 5, and 1. 2, 1, that is 1. 4, 3, and 4, 1, that's 2. 3, 1, that's another 1. 5, 1, another 1. So 1, 2, 1, and 1, that will give us 5. Okay, then 3, 1, 4, 2, 5. 3, 1 and 3, 2, that will be 2. 1 is the smallest, so there will be no inversion. 4, 2 is another 1. Okay, 4, 5, there is no inversion. 2, 5, there is no inversion. So 2 and 1, that would be 3 inversions. Okay, so for the permutations of S, 1, 2, 3, and 4, let us indicate the number of inversions. So the number of inversions. How will you do that? Okay, so the number of inversions for 1, 2, 3, 4, that will be obviously 0 because it is in its natural order, so there will be no inversion. 1, 2, 4, 3, 4, 3, that will be 1, 3, 2, that's another 1, 3, 2, and 4, 2, that will be 2, 4, 2, 4, 3, that will be 2, 4, 3, 4, 2, and 3, 2, that will be 3. Okay, 2, 1, 3, 4, 2, and 1, that will be 1, 2, 1, and 4, 3, that will be 2, 2, 1, and 3, 1, that's another 2, 2, 1, 3, 1, and 4, 1, that will be 3, 2, 1, 4, 1, 4, 3, that will be 3, 2, 1, 4, 3, 4, 1, and 3, 1, that will be 4. For 3, 1, 2, 4, 3, 1, and 3, 2, that will be 2, 3, 1, 3, 2, and 4, 2, that will be 3, 3, 2, 3, 1, 2, 1, that is 3, 3, 2, 3, 1, 2, 1, and 4, 1, that will be 4, 3, 1, 3, 2, 4, 1, and 4, 2, that will be 4, 3, 2, 3, 1, 4, 2, 4, 1, and 2, 1, that will be 5. Down to the last column, or the last set of permutations, 4, 1, 2, 3. 1, 2, and 3. 4, 1, 4, 3, 4, 2, and 3, 2, that will be 4. 4, 2, 4, 1, 4, 3, and 2, 1, that will be 4. 4, 2, 4, 3, 4, 1, 2, 1, and 3, 1, that will be 5. 4, 3, 4, 1, 4, 2, 3, 1, and 3, 2, that will be 5. 4, 3, 4, 2, 4, 1, 3, 2, 3, 1, and 2, 1, that will be 6. Okay, so that completes the data for the permutations of S as far as the number of inversions is concerned. Okay, let us have another definition. A permutation J1, J2 up to Jn is said to be an even permutation if it has an even number of inversions. Okay, a permutation J1, J2 up to Jn is said to be an odd permutation if it has an odd number of inversions. So in the like manner, a permutation J1, J2, Jn is said to be an even permutation if it has an even number of inversions. Okay. So we can classify now each of the um, permutations of S. So indicate whether the permutation is an odd permutation or an even permutation. Will you complete? Will you complete the classification for each of these permutations? Okay. So for 1, 2, 3, 4 is 0. So it must be even. 1, 2, 4, 3 S1 inversion. So that is an add, even, odd. 2, 1, 3, 4 S1 inversion. So it's add, even, odd, even. 3, 1, 2, 4 has two inversions. So it's even, 3 is odd, 3 is odd, 4 is even, 4 is even, 5 is odd. Finally, 4, 1, 2, 3 has three inversions. So it is odd, then even, odd, and even. Okay. At this point, will you count on the number of odd and even permutations? So number of odd permutations and number of even permutations. Okay, so for odd permutations, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 odd permutations. Even permutations, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. As you can see, there are equal numbers of even and odd permutations. Okay, so we can summarize that for S equal to 1, 2, 3 up to n, there will be n permutations or n factorial permutations. And what else? There are n factorial over 2 odd or even permutations. Okay. We shall now define the determinant of an n by n matrix. Given an n by n matrix A equal to A, I, J. So let S be the set containing the numbers 1, 2, 3 up to n. The determinant of A denoted by the absolute value of A or that of A is defined by the summation of plus minus J sub 1, or it should be A sub 1 J1 times A sub 2 J2 times A sub 3 J3 up to A sub n Jn, where the summation is taken over all permutations of S. The sign is positive if the is even and negative when it is odd. Okay. So we shall take the summation of the products of the elements A1J1, A2J2 up to ANJN, preceded by either a positive or a negative sign depending on the permutation J1 up to Jn. Remember that Aij represents an element of matrix A. The first subscript represents the row and J represents the column. So if we are to take the first element A1J1, that means that this is the element coming from the first row and the column Ji or column J1. And J1 is the first number that appears in the permutation J1, J2 up to Jn. Alright? For the second entry or the second element, it is A sub 2J2, meaning the element comes from the second row and the column from where it comes from is column J sub 2, which is actually the second entry or the second element in the permutation J1, J2 up to Jn. And we continue on and on until the last element ANJN. ANJN means that it comes from the last row, the nth row, and JN column. JN represents the last entry in the permutation J1 up to Jn. Okay? So we will do that for all the permutations of S. Notice also that there is one entry coming from each row. From row 1, A1, from row 2, A2, from row 3, A3, up to row N, A sub N. The column position J1, J2, J3, Jn is dictated by the permutation J1 up to Jn. So, if your S is, or if the matrix given is a 4 by 4, so 1, 2, 3, and 4, one of the addends is A1, J1, A2, J2, A3, J3, and A4, J4. So, if the first permutation that we are going to use is the permutation 1, 2, 3, 4, we will simply replace J1, J2, J3, and J4 by 1, 2, 3, and 4. So that becomes A11, A22, A33, and A44. If you are going to use the permutation 1, 2, 4, 3, oh, by the way, for the permutation A1, 2, 1, 2, 3, 4, it is an even permutation, so it must be preceded by a positive sign. Okay? If you are using the permutation 1, 2, 4, 3, so how many inversions are there? There is only one, and so that is an odd permutation. So, A1, J1, A2, J2, A3, J3, and A4, J4 will become, so let us replace this. It will become A1, 1, A2, 2, A3, 4, and A4, 3. Okay? So, the first subscript will always start from 1. So, A1, A2, A3, and A4. The second subscript will come from the permutation. And since 1, 2, 4, 3 is an odd permutation, it is preceded by a negative sign. Okay? So we are going to multiply an element from the first row by an element from the second row, by an element from the third row, and by an element from the fourth row. Now, the exact location of those elements will be dictated by the permutation. So, if S is 1, 2, 3, 4, we know that there are 24 permutations. So that means that we will replace J1, J2, J3, J4 by each and every permutation of S. So there are 24 all in all. But in our example, let us start with a 3 by 3 matrix. Okay, we are given matrix A. Let us just label them as A11, A12, A13, A21, A22, A23, A31, A32, and A33. Alright, so we start by writing the set S. Since it's a 3 by 3, the elements of S are 1, 2, and 3, and the permutations are 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. Let us indicate the number of inversions. That will be 0, 1, 1, 2, 2, and 3. So what is the classification? For the first inversion 1, 2, 3, it is even and then odd, odd, even, even, and odd. There are 3 odd and there are 3 even permutations. Okay, so let us apply the definition. The determinant of A is equal to the summation of plus minus A1 J1 times A2 J2 times A3 J3. Alright, so let's start with the first permutation 1, 2, 3. So we will simply replace J1, J2, and J3 by the numbers 1, 2, and 3 respectively. So that will be A1, 1, A2, 2, A3, 3. This J1, J2, J3 is replaced by the numbers 1, 2, 3. And since it is even, it must be positive. Then, we go to the next. 1, 3, 2. Since it is odd, it should be negative. And then A1, A2, A3. The second subscript will be replaced by the numbers 1, 3, and 2. So, 1, 3, and 2. We go to the next one. 2, 1, 3. It is odd, so it should be negative. A1, A2, A3. 2, 1, 3 will replace J1, J2, and J3. So 2, 1, and 3. Next, even. So it must be plus A1, 2. Then A2, 3. A3, 1. Next, 3, 1, 2. Even, so positive. That will be A1, 3. A2, 1. A3, 2. Finally, minus A1, 3. Then A2, 2. And A3, 1. There. So if these are actual digits, you simply replace all these by the given numbers or the given digits. Okay, at this point, this expression is exactly the same expression that we will get if we will use the so-called basket weaving method. Basket weaving method of finding the determinant of a 3 by 3 matrix. How is that? You multiply the elements along the diagonal A11, A22, and A33. Okay? So, A11, A22, and A33. So, for the diagonal to the right, it will be positive. Okay? Next, we multiply A12, A23, and A31. Okay? I hope you see that. A12, A23, A31. So, plus A12, A23, A31. Then, A13 multiplied to A21, A32. A13, A21, A32. Then, for the diagonal to the right, it will be negative. So, negative A13, A22, A31. Next, A11, A23, A32. So, negative A11, A23, A11, where am I? A11, A23, and A32. Finally, that will be A12, A21, A33. A12, negative A12, A21, and A33. And these elements are actually the same elements that you will find in applying the definition for the determinant of A. Okay? So from here on, if you are to get the determinant of a 3 by 3, you need not list down all the elements. No? You can just multiply the elements along the diagonals, and that will give you the determinant. So let us have an example. Let us find the determinant of A. So the determinant of A is equal to, let us use the basket weaving method. 3 times 0 times 1. 3 times 0 times 1. Plus negative 1 times 1 times 1. Negative 1 times 1 times 1. Plus 2 times 2 times negative 1. 2 times 2 times negative 1. Next, minus 2 times 0 times 1. 2 times 0 times 1. Minus 3 times 1 times negative 1. 3 times 1 times negative 1. Minus negative 1 times 2 times 1. Negative 1 times 2 times 1. Okay? So, since one of the factors here is 0, that will be 0. Same thing here. So, negative 1 times 1 times 1 is negative 1. 2 times 2 times negative 1 is negative 4. Negative 3 times 1 times negative 1 is positive 3. Negative 1 times negative 1 times 2 times 1 is positive 2. So 3 and 2 is 5 minus 5. That gives us 0. Okay? So will you try? Will you try finding the determinant of matrix P? 2, negative 1, 5, 3, 2, 1, 0, 1, and 3. Okay, so the determinant of b is equal to 2 times 2 times 3, that will be 12. Negative 1 times 1 times 0, that will be 0. And then 5 times 3 times 1, that will be 15. Okay, then minus 5 times 2 times 0, that will be 0. Minus negative 1 times 3 times 3 is negative 9, so it becomes positive 9. And finally, minus 2 times 1 times 1 is 2. So that will be 27. 36 minus 2 is 34. So again, 2 times 2 times 3 is 12. Negative 1 times 1 times 0 is 0. 5 times 3 times 1 is 15. Minus 5 times 2 times 0 is 0. Minus negative 1 times 3 times 3 is negative 9. So positive 9. Minus 2 times 1 times 1 is negative 2. So 12 and 15 is 27 plus 9. 27 plus 9 is 36. Minus 2 is 34. Okay?